Okay, this section is about the greenhouse effect. So what we want to know is, what is the greenhouse effect? What are greenhouse gases? How do they work? What does it mean when we have too much of them? So let's take a look at the first diagram in your packet, which explains the greenhouse effect. Now, what you've got is some blank squares here. And what you need to write down is what happens in each section here. And this is number 1. So what happens first in the greenhouse effect? You have incoming solar radiation, which is made up out of UV light and visible light. If you remember the electromagnetic spectrum, there are different wavelengths of different waves all along that, and UV light and visible light are one part of the electromagnetic spectrum. So that comes in from the sun. Okay, the second thing that happens is that a third of that UV light and visible light is reflected back into space. So here's my incoming solar radiation. Here is it getting reflected back into space. Okay, so what happens next? The remaining light, the one that's not reflected back into space, is absorbed by clouds and also the surface of the planet. And the clouds and the surface of the planet become warmer, and they emit what's called infrared radiation, different wavelength of electromagnetic spectrum. It's a whole different one. So it is not the same as the UV light and the visible light. It's called infrared, and see how it's spelled INFRA, infrared radiation. Okay, that gets emitted back into space. Okay, that infrared radiation is either absorbed by the greenhouse gases that are in the air, or it's emitted back into space. So what you've got here is a whole little diagram. Here's my incoming UV and shortwave radiation. Some of it reflected, some of it emitted back as infrared and then absorbed by greenhouse gases, or emitted back into space, or comes back to the Earth again. And so that is how the greenhouse effect works. Now, the last one here says more greenhouse gases equals more infrared radiation absorbed and emitted back to Earth. So this is why it's making us warmer. If we have more greenhouse gases, we tend to send more, absorb more, send it back to Earth, make us warmer. All right, this is a diagram here on page 5 that you're going to have instructions posted on how to fill this out. So this is in your packet, and what you want to do is color this and cut out some pictures that go with it. And it'll tell you on the diagram instructions how to complete this whole thing. And it is basically like a schematic of the different types of gases that are emitted by different types of human influenced situations and what happens to them. So stay tuned for that. That's in your module on the greenhouse effect. Okay, so this greenhouse effect process should be in equilibrium. So short-term inputs could be higher or lower, which causes global warming and cooling, ice ages, or periods of warming. And so this graph shows you that. Glacial or interglacial cycles over the past 450,000 years. So take a look at what happens here. The temperature going up and going down. So interglacial, temperature goes up. Glacial, temperature goes down. Interglacial goes up. Glacial goes down. So ice ages, non-ice ages, ice ages, non-ice ages. This has happened in cycles for many, many, many years. Okay? So what are greenhouse gases? If you take a look at the chart here, a page after the diagram, what are greenhouse gases? So nitrogen and oxygen are not greenhouse gases. They make up 99% of the atmosphere. We don't include these in the greenhouse gases. So here are all the other gases that we do include, and we call these greenhouse gases. One is water vapor, which absorbs more infrared radiation than anything else, but because water vapor is so short-lived, it doesn't persist, and therefore it's not going to hang around too long, so it's not too much of a problem. CO2 is a greenhouse gas. Carbon dioxide. CH4 or methane, a greenhouse gas. Nitrous oxide, N2O, a greenhouse gas. Ozone, another one. And CFCs, which are chlorofluorocarbons, which you should have learned about when you looked at the stratospheric ozone depletion. These are not natural, these are man-made chemicals. Okay, so how can we remember those? We can do this little mnemonic called We Call Our Mothers Now, water, CO2, ozone, methane, and nitrous oxide. See if you can remember that. Make up another one if you'd rather, but you can put that in the box right there and write that down, and maybe that'll help you remember what all the greenhouse gases are. Okay, now this is super important. Put a star by this. Without greenhouse gases, the average Earth temperature would be 0 degrees Fahrenheit. Why? Because all of that nice infrared radiation and all of that heat would escape back into space and it would be gone. It would not be on the planet. We could not live here. So the greenhouse gas, the greenhouse effect is good. By itself, it's good. Our actual average temperature on the Earth, 57 degrees Fahrenheit, if you average winter and summer and all those things together. Without these gases, we would be freezing. We could not live here. Okay, so what is the proportion of greenhouse gases in the atmosphere right now? And what is the potential for them to participate in warming? Like, how good are they at trapping heat and warming the Earth? We're going to start with water vapor. The concentration here depends on the temperature. It goes up and down. The concentration of CO2, 419, might be a little higher than that right now, 419 parts per million. Methane, 1.8 parts per million. Nitrous oxide, 0.3 parts per million. And CFCs, 0.9. Now, what is the global warming potential of these gases? So what does that mean? It's about 1. Here for water vapor, it's a little bit less than 1. So let's take a look at the others. If we count CO2, we're going to count that as 1. So we're going to kind of compare everything off of CO2. So let's say CO2 for 100 years has a global warming potential of 1. So that's kind of a constant. So methane has 25. So what does that mean? Methane is 25 times more, 25 times better at warming or trapping those gases and making us warmer than CO2 is. So it's a lot worse. 300 times for nitrous oxide and 1,600 to 13,000 times for chlorofluorocarbons. And now, how long do these things last in the atmosphere? So water vapor, about 9 days. Variable for CO2, but several years. Methane, about 12 years. Nitrous oxide, 114 years. And CFCs, 55 to 500 years. So the question here is, what is the global warming potential? How much a molecule can contribute to the global warming over 100 years relative to a molecule of CO2? And this depends on how well it absorbs infrared radiation and how long it persists. So take a look at this chart here. I want you to compare all these numbers. How much of these gases are in the atmosphere right now? What is their potential for warming? How long do they last in the atmosphere? All of those things have to be taken into consideration to figure out how much we're worried about each of these different gases. So the potential warming plus the concentration of them is going to equal the total effect that they would have on us in the long term. So what I want you to do is rank the GHGs in order of potential. This should say in order of potential. Which greenhouse gas has the biggest effect and why? Why are man-made greenhouse gases like CFC so worrying if their concentration is so low right now? And why is water vapor not a concern in terms of causing climate change? Now, if you're watching this video and you missed class, then just stop the video now. See if you can answer those questions. Think about it. Go back to the chart right here and take a look at the chart and see if you can answer these 4 questions. Now, if you're back here and you turned the video back on, here are the greenhouse gases in order of their potential. CFC is the highest, nitrous oxide, methane, CO2, and water vapor. That is the potential for warming. However, which one has the biggest effect and why? And the answer to that is CO2. And the reason for that is it has the largest effect of any other greenhouse gas because the concentration of it in the atmosphere is so high right now, and it's going up so much very, very quickly. So it doesn't have the greatest warming potential, but we just have more of it than anything else. And so that's why when you hear about controlling climate change and controlling global warming and all of that, you mostly hear about CO2. Okay, why are man-made greenhouse gases like CFC so worrying if their concentration is so low? It's because their warming potential is so high and they're very persistent in the atmosphere. So if we were to increase our CFCs in the atmosphere by a tremendous amount, we would not only hurt the ozone layer, but we would also help contribute to global warming. Why is water vapor not a concern? Because water vapor has such low persistence in the atmosphere, it doesn't stay around very long. So it just breaks down, cycles quickly through the water cycle, goes away. So it doesn't really contribute to long-term change. Okay, so here are some just pictures of things that we can take a look at. We've got gas bubbles trapped in the ice here. And these are basically natural sources of greenhouse gases. So where do these greenhouse gases come from? Naturally. Okay, so we've got some gas trapped in ice. We've got volcanoes, ash reflecting incoming radiation, so that actually has a cooling effect. But when the volcano erupts, you do get some greenhouse gases out of that. And you've got decomposition and digestion. So you really have two things on your paper there, and one is the volcanoes, and the other is decomposition and digestion. So this is when dead organic matter is converted into CO2. Unless there's not enough oxygen. And when there's not enough oxygen, it's converted into methane. So this is like a wetland, and you see dead and decaying matter underneath all this water and grass, converted into CO2. But then if there's not enough oxygen, it will get converted into methane, which happens more often in wetlands. So sources of methane in nature: wetlands and termites, through decomposition and digestion. And then another source of natural greenhouse gases is denitrification. So we get a little nitrous oxide from that. And here's my denitrification reaction sequence. I've got nitrate, then it turns into nitrite, nitric oxide, nitrous oxide, and nitrogen gas. So before, in the nitrogen cycle, when we talked about denitrifying bacteria and denitrification, we basically just told you that that nitrate and nitrate ends up turning into nitrogen gas. And yes, it does, but there are a couple steps in between. And so with that, we get a little nitrous oxide. So that's naturally a source of nitrous oxide. And that's where that happens for the denitrifying bacteria. And then we have evaporation and evapotranspiration that contributes water vapor to the atmosphere, and that's natural also. Now, what are some anthropogenic or human-caused sources of greenhouse gases? First one here is fossil fuels, contributes CO2, methane, and nitrous oxide. Now, particulate matter in the air lowers the reflective ability of the earth, and that's through black soot. So then that also means that more is absorbed and less is reflected. Agriculture is another source of greenhouse gases through a couple different ways here. Over irrigation. So if we water too much, it turns out making low oxygen, so methane might be released in some agricultural situations. And then we have fertilizers, which do go through some denitrification, which would add nitrous oxide to the atmosphere. And then we have livestock. Cattle and sheep would release methane into the atmosphere, mostly through burping. And they just, because they eat the grass and they do that sort of thing, and then they release all that methane. You can actually measure that, and it's quite a lot. So the agriculture industry does contribute a significant amount of greenhouse gases to the atmosphere. And then deforestation would be a human-caused source of greenhouse gases, and that's only because if you cut down the trees, you're going to have less photosynthesis, so you're going to have more CO2. So if I don't have these trees around, they're not taking in the CO2 like they normally would to do photosynthesis, and therefore I'm going to have more of it. If I burn the trees, I'm going to release particulate matter, methane, and nitrous oxide as well. So if I do slash and burn, cutting down of rainforest so I can make land for cattle, there's all kinds of problems with that. Not only am I not having the trees to take up CO2, but I'm releasing all this other stuff when I'm burning them. And then if I have cattle there, then that's more greenhouse gases. And then landfills do contribute a little bit of methane to the atmosphere. which is produced from food and garden waste that's kept in an anaerobic condition without oxygen in here. So see, when I have my landfill truck driving along, he's compacting the soil here, which is removing air in the landfill because I'm trying to create save space. That creates an anaerobic environment, and then that's releasing methane into the atmosphere. And you know that sanitary landfills sometimes try to capture this methane, so they're actually trying to work on that. And then I have modern chemicals like CFCs. HCFCs have replaced CFCs, but they're also greenhouse gases. So we knew that the CFCs were causing a hole in the ozone layer. So through the Montreal Protocol, we have tried to reduce that quite a bit, and we've actually fixed the hole in the ozone layer, but we also have replaced them with some things called HCFCs sometimes, which also ends up being a greenhouse gas. Okay, so human sources of methane here, what are they? Fossil fuels, livestock, and landfills. So if you take a look, fossil fuel is in the blue and livestock farming is in the red. And look, that's a big, big chunk here. And landfills is another really big chunk. Biomass, rice agriculture, biofuels do contribute a little bit, but not nearly as much as those three right there. That's 80%. Okay, what are the nitrous oxide emissions by source in human-caused nitrous oxide emission? Fertilizers, agricultural soil, and fossil fuels, all contributing to about 95% of our nitrous oxide in the atmosphere from humans. And then CO2, fossil fuel combustion is 95%, so that's an awful lot. So what happens when greenhouse gases increase? Can you pause the video and figure out where you could put all of these phrases at the top? Thermal expansion of ocean water, disease vectors spreading from tropics to poles, rising sea levels, population movement, global climate change, population dynamics, excess greenhouse gases in the atmosphere, and melting ice sheets. So pause the video, take a minute here, and see if you can figure out a flow chart that would explain all of these terms by writing them in your packet. Okay, let's take a look at the answers here. Excess greenhouse gases starts us off. So if we have too many of those greenhouse gases, what does that lead to? It leads to climate change because we're having more heat and more infrared radiation being absorbed, which is warming the earth, which leads to the climate changing. Okay, what can climate change lead to? A little preview here of climate change. It can lead to rising sea levels. It can also, from rising sea levels, how does that happen? Melting ice sheets. So when ice melts, you're going to raise the sea level, and also thermal expansion of water will raise the sea level. It also leads to spread of disease vectors. So diseases getting into places where they previously could not because the climate was not correct for them, and now they can spread to lots of other places. These two things, rising sea levels and spread of disease vectors, are going to lead to changes in population dynamics and population movement. Think about little tiny islands out in the Pacific Ocean or somewhere where the sea level is rising. Whole communities and societies then might have to move and leave their home of generations. They may not have an island left anymore. And then if you've got a lot of disease vectors spreading, it's going to lead to population movement and population dynamics changes too. So that's a little preview there of climate change. We're going to do a little bit more with climate change with some notes and a web quest. So stay tuned for that. And in your section on greenhouse gases in your modules, there are a couple of videos linked that you want to watch there just as a nice summary of what greenhouse gases are all about. Thanks for listening.